Good morning, good afternoon, good evening. Welcome to the Documenting and Preserving Languages in Unicode webinar. My name is Encoding, and I'll be the moderator for today's event. As a reminder, this session is being recorded and will be posted on the Unicode Consortium YouTube channel. Use the chat box for questions to the team. We'll spend the first 45 minutes today hearing from Debbie and Andrew, and after that, we'll have about 10 minutes for Q&A. Let me introduce you to our webinar team. Debbie Anderson is the chair of the Script Ad Hoc Committee in Unicode. Andrew Glass is a principal product manager at Microsoft and serves as the CLDR keyboard subcommittee chair. Karen Dawson is the community engagement and events manager at Unicode. And I'm Encoding Charan, and I serve as the vice chair of the community engagement team. All right, let's get started. Over to you, Debbie.
Thank you, Encoding. Let me share my screen. All right, great. So as Encoding mentioned, I'm chair of the Script Ad Hoc. I'm also a researcher in the Department of Linguistics at UC Berkeley, and have been running a project called the Script Encoding Initiative. I'm here today with my colleague, Andrew Glass, to talk about documenting languages with Unicode, fonts, and keyboards. This talk is part of a series of events that's put on by the Unicode Consortium. My talk will take you through the basics of character encoding in Unicode, and Andrew will then discuss fonts and keyboards, which are other key pieces that are needed to access characters for writing the languages of the world. There are many details about Unicode that can't be covered in this short webinar, but I'll point you to some resources you can explore for more information. I'll speak for about 15 minutes, and then I'll turn it over to Andrew. And as Encoding mentioned, we'll have time for questions. And please be sure to write your comments or questions in the chat box. Work on documenting and preserving languages of the world comes at a critical time when languages are in danger of disappearing, and the written materials in these languages can be lost or destroyed due to climate change, war, or other factors. This map comes from the Endangered Languages Project, using colors to designate the status of various languages. The red and orange colors indicate severely endangered or endangered languages. For linguists and language users, being able to document languages and preserve written materials in that language ensures the languages of the world can be studied into the future and, in some cases, revitalized. Unicode underlies all electronic text communication today, and hence is vital to preserving text used to write languages and for linguists to be able to describe them. It allows text to be sent and received reliably without the text getting garbled. It also makes it possible to copy and paste. As an international standard, it provides a stable means of representing text so it can be archived and saved for the future. As my colleague and I will explain, Unicode ultimately provides the basic components needed so user communities themselves can create text resources and materials and be able to interchange them electronically. Unicode also provides the basic elements needed by linguists to document languages. But a critical first step is getting the characters that are used to write and describe languages into Unicode. Linguists and others working with various languages may employ a variety of characters, such as the International Phonetic Alphabet, other phonetic systems, technical notation, transliteration, and different orthographies. Or a linguist or community member may be developing a new orthography for a language. A particular problem for linguists and language users is how to access the characters they need, but which are not found on a computer or device. One workaround they have used is to create their own font using software like Fontographer. As an example, the Narom font, shown on the right, put the capital letter gamma in the spot that another font had assigned the cent sign. The problem with this approach is that the Narom font relies on the font creator's private knowledge, but the person receiving the text may not be privy to the same information. So the text on the right-hand side on the top, which uses the Narom font, may well come out as the text on the bottom. The result of using a non-standard hacked font, such as the Narum font, is that exchanging data will not be reliable, meaning you can't be sure that the text you sent will be received as intended. In addition, with a non-standard font, apps often won't behave as expected, and you can't switch fonts to get the same text. In short, there's no interoperability of data. The solution is Unicode, a single international standard. Unicode has universal coverage. It's supported on all modern browsers and operating systems and provides interoperability of data. Unicode also provides comprehensive coverage. In theory, it should provide all the characters, historic and modern, that are needed to write languages. At least that's the goal. In short, if you want to represent text today on computers and devices, or you're working with a community that will be using electronic devices for their language, it's important to be using Unicode. The latest version is Unicode 15.0, which contains over 149,000 characters and 161 scripts. The majority of characters are Han ideographs with over 98,000 characters. Besides characters used in scripts, Unicode also includes many symbols. Because Unicode has space for over 1 million characters, there's still room for 825,000 more characters. The next full version of Unicode will be Unicode 16.0, slated for release in September 2024. The Sunawar script used in Nepal and Sikkim, India, is shown on the top of the primer on the right. It's one of the scripts that's scheduled to appear in Unicode 16.0. Work continues on other scripts for future versions, including the historic script Seal, Jurchen, and Maya hieroglyphs. On the next set of slides, I'm going to go over some of the Unicode basics. When referring to a Unicode character, there are two unique identifiers, a name and a number, called a code point. An example is Latin small letter esh with double bar, and its code point is U plus 1DF0B. Unicode code points are referred to by U plus, followed by 4 to 6 hexadecimal digit. Unlike the Unicode name and code point, the representative glyph can be changed within some limits. To see the Unicode repertoire of characters, you need to go to the Unicode code charts. I will show you how to access them shortly. The code charts include a graphic chart with glyphs or images of each character, followed by the names list. The names list has a code point, a glyph, name, and it may include some additional information that identifies the character and may point to its use or purpose. The Unicode Consortium website has two main web pages that serve as a portal to information about Unicode. A general one, which has emoji and some other characters on it, and then a technical website. The technical website is the one that I typically use, and it has a link to the code charts page. The technical website also has a link to the latest version of the Unicode Standard core specification. The core spec is the text with a general introduction to Unicode, conformance and implementation guidelines, and chapters on all the characters arranged by script or class of characters. Fundamental to Unicode are a number of basic principles. Unicode defines the basic character's identity with a unique name and code point. These will never change, and the characters cannot be removed once they're published in Unicode. As I mentioned earlier, the glyph of the character can, in some cases, be changed within limits. Besides the name and code point, characters have properties that define its identity and semantics. For example, such information includes the relationship between the character's uppercase and lowercase, and information on whether a given character is a number, a mark of punctuation, a symbol, or a letter. In Unicode, characters are organized into blocks of related characters, typically by script. You can see on this slide the many blocks of Latin characters, which includes IPA and phonetic extensions. The web page this snippet comes from lists the 161 scripts. There are also several core design principles in Unicode. These are important to point out because they're often sources of confusion. If a letter is used by the same script but in different languages, then the character is unified. In other words, there's just one Latin small letter A in Unicode, although it's used in English, French, Spanish, German, and many other languages. There's no French small letter A or German small letter A. So the approach to encoding Unicode is really the focus on scripts rather than language. But in the case of different scripts, characters are not unified, even though the shapes may appear to be similar. So Latin capital letter A is not unified with Greek capital alpha or Cyrillic capital letter A, though they appear the same. These are three different characters. Unicode encodes characters, not glyphs. Definition of a character is an abstract unit containing textual information. Glyph, on the other hand, is a graphic image used in presentation. So the Latin small letter character A has many glyphic appearances. You have the two-story A, and italic A, etc. These are all clearly Latin small letter A, the same character. The relationship between characters and glyphs may not be one-to-one. Arabic letter He, for example, is a single character in Unicode, but has different shapes depending on its position. Unicode assumes the font and rendering engine will handle these different shapes. Characters may not necessarily be the same as text elements in a writing system. For example, a C with a tilde may count as a separate letter in a writing system, but Unicode is made up of two different characters, small letter C and combining tilde. Similarly, CH, which in Slovak is one letter in the alphabet, is two characters in Unicode. Another principle is that of dynamic composition. Characters can combine in a sequence to create a complex text element. Here you have a C with 5 combining diacritics. Unicode also supports older legacy standard character sets, namely those in wide usage as of May 1993. This principle required many compromises with other design principles. And this explains why you find in the Unicode code chart some precomposed characters, that is, single characters made up of a base character and diacritics. An example is Latin small letter A with acute. It's included because it was in the earlier ISO 8859-1 standard. Drawing on the idea of dynamic composition are a few related points. Representing characters with diacritics is done via sequence of characters. As I said, the base character with the combining diacritics. If two marks are in a similar space, such as above a letter, the order makes a difference. In this example on the slide, you see that the closest diacritic to the base letter appears first, then the next one above it. But if the marks don't interact typographically, putting the marks in different orders doesn't make a difference. On this slide, there's a diacritic above and below, and it doesn't make any difference which order the characters appear in. A text element can have several multiple representations, and Unicode defines two: a canonical equivalent, which means they are considered the same, and a compatibility equivalent, which means they mean the same in some, but not all circumstances. Software normalization is used to identify and handle equivalent sequences. And you can read more about this in this Unicode Standard and Unicode Annex number 15. So in practical terms, the first step to be able to use Unicode is for the characters to be published in the standard. There's a process for proposing characters, and the process can take at least 2 years. So the first thing is to write a Unicode proposal, and I have a snippet of a proposal here for 2 Latin characters. The proposal then gets reviewed by the script ad hoc, and that's true at least for characters that are not emoji or CJK ideographs. Those are handled by different committees. Then the proposal needs to get approval by the Unicode Technical Committee, and finally the characters get published in a version of Unicode. When writing a Unicode proposal, I recommend using a proposal template, which outlines information that needs to be included. There are 2 templates, one to add a character to an existing script in Unicode, and a second one for proposing a new script. Proposals that are complete with the required information will be reviewed by the script ad hoc. There are often questions that come from the script ad hoc requiring proposals to be revised. Typically, proposals go through many revisions before the script ad hoc deems them ready to go to the next committee. A proposal needs to make a strong case for the characters or script to be added. Is there a user community today that needs the characters to write their language that can't already be done with current characters? Relatively recently created scripts generally have a high hurdle to overcome. They must demonstrate that the script has been accepted and used by the user community. Print publications, preferably going back at least a few years, are needed, and the repertoire of characters should be stable. In the case of a language that does not yet have an orthography, there's a set of recommendations in the Unicode Technical Note number 19 on which characters to use. The other coordinated pieces that are needed after characters in Unicode are fonts, keyboards, and software support. Before I turn the floor over to Andrew, I'd like to invite anyone interested to get involved. There is a need for linguists and experts to help write proposals and review them. This slide contains links to various resources for working on proposals. So with this, I'd like to thank everyone for viewing my portion of this, and now I'm going to turn it over to Andrew.
Great, thank you, Debbie. I will just share my screen. So yes, good day, everyone. My name is Andrew Glass, and I'm the chair of the CLDR keyboard subcommittee. I won't go into exactly what that is in today's talk. I am also a product manager at Microsoft, and I have the privilege of working on keyboards and fonts on the Windows platform. So the best part of my job is that I get to work on enabling writing systems, both fonts and keyboards, and have done that for a number of languages, starting with Pakpa and Myanmar and Javanese and Unko and ADLaM and a great many. So it is a wonderful job, and I feel very connected to the overall mission of Unicode, enabling people to use computers in their language. And so today, for about the next 20 minutes or so, what I want to do is introduce some of the core elements of Unicode keyboards and fonts. And the emphasis of what I will cover is on really what you can do with keyboards and what you can do with fonts, rather than actually how to make them. How to make a keyboard and font is really a much longer topic, and maybe we can explore that in a future occasion. So for my goal today, I simply want to raise awareness of the different capabilities of Unicode compliant OpenType fonts, as well as commonly available keyboard solutions. And my hope is that this will help you further your interest in supporting the languages that you care about using Unicode. But before getting started, I'd like to do some elementary grounding on language, computers, and Unicode, which will help frame how I think about the role of keyboards and fonts. So we're interested in human language, and the fundamental components of listening and speaking, reading and writing are common to all. Listening and speaking have very special functions when it comes to enabling on computers. Oh, I'm sorry.
Yes.
I didn't finish sharing my screen. Sorry about that. Thank you for the prompt. So listening and speaking have very specialized applications, and I won't talk about those today. But I want to talk about reading and writing. And on the computer side, I think of computer as a tool for storing, transmitting, and computing with text, with data. And in our case, what we're interested in is language data. And this, the sort of the common language of managing language data when it comes to storing, transmitting, and computing, manipulating data, is Unicode, as Debbie introduced. So really, the job of human-computer interaction with language data is dealing with language data coming out from the computer system, and that is a font. And so the role of the font is to visualize language data stored in a computer. And conversely, the role of a keyboard is to input language data in human terms into this Unicode layer that the computer understands. So together we have these complementary and opposite systems. We have fonts for display, for reading, and we have keyboards for writing. And so what I want to sort of ground here that the fonts have always been a very key focus of Unicode, and they have been inherently designed to be natural for language communities. And language communities should not pay any attention to the details of Unicode that underlie them. On the keyboards, on the other hand, have often suffered from requiring some knowledge of Unicode principles in order to successfully input text. And so there's a learning curve with using a keyboard that is not really there on the font side. And so a number of us in this keyboard CLDR committee are really motivated by this idea that we need to move the human zone really above this and separate it from the Unicode layer. And so that the vast majority of language users should really only focus on what makes sense to them in terms of fonts and keyboards and what they know about their language, and should really be insulated from this Unicode layer. And so we know that we will do our job well, and Unicode will be successful when language communities can really use the tools in this way. So let's talk about fonts. Here are some examples of text in printed form. And so it is the role of fonts to really display in all of the variety the capabilities of the printed form and to a lesser extent the written form. And as Debbie introduced, there can be stylistic variation, but a very important grounding of fonts is that when there is a single Unicode sequence, a fixed Unicode sequence, really there should be a consistent visualization of that with a font. Now, with 161 scripts already supported in Unicode, the range of orthographic requirements that is needed for those many different writing systems and the range of solutions that have already been developed in order to support those many requirements is actually amazing. And so when it comes to thinking about a new script like Mayan, in terms of the Unicode process, when we look to how we would go about encoding something like Mayan, there are a lot of solutions already across the spectrum of these 160 plus scripts in Unicode that give us the tools to think about how to go do that. On the right-hand side here are just a selection of some of the capabilities of fonts that are needed in order to represent just the writing systems that you see there in the examples on the left side of the screen. And we'll look into each of these in a bit more detail. So here is a text, a printed text, and obviously we want to render it in Unicode. And so the first part of a font is this job of character mapping. There is a sign, an E with a macron, and we want to ground that in the text. And so we're going to use Unicode code point 0113. So we need a suitable font. We need a font that has a picture of this Unicode character 113. And so essentially a font is really a collection of images each one mapped to a Unicode code point. And these glyphs are the pictures themselves. In most fonts today, these pictures, these glyphs are vector outlines, so mathematical expressions for an image. And the value of this is, of course, that we can scale these images, make them smaller or larger without compromising the visual appeal of the original text, the way the font designer created it. And so a lot of the art of creating a font really comes down to being able to create these vector outlines. And one does this using font software, such as Fontographer was the example that Debbie showed earlier. So when we extend from this simple model of fonts that consist of images, these vector outlines, we need to introduce some capabilities, and the core capability is this glyph positioning. Creating a relationship of how do you position one of these glyphs relative to another. So in this case, we can see the image for the outline of E, and we can see a bunch of shadows in this font editing software. And what these shadows are is realizations of where various combining diacritics would land based on information that is in this font. So you can see what we can do here is we can specify there is an anchor point somewhere around this E, and there are various anchor points for different kinds of diacritics. And so the glyph positioning establishes a rule by which you say this group of combining marks are positioned relative to a base sign on this particular anchor. And so a font designer can create a lot of base signs and place anchors on them that allow combinatorially a lot of the orthographic needs of that writing system. And so here, the font designer doesn't need to be aware of ultimately what the linguistic needs might be for a particular use case of the font, because combinatorially they can support all of them up front. And so this is a great, one of the powers of open type fonts and Unicode together. Now, another core capability of Unicode and open type fonts is this concept of glyph substitution. So many of the glyphs in a font will be not directly mapped actually to a Unicode code point, but will be accessed by the font based on context. And so what we see here is this is Mongolian text written vertically. And Mongolian is what's called a joining script, where the shapes of the basic letters adapt depending on where they are in the word. So in this case, you can see there is this letter Mongolian E, and I've rotated it from the Unicode code chart so that it looks like the vertical form. And you can see it occurs at the beginning and end of the word, but the shape of the last form of the final E has changed radically. And this is done with a rule, a substitution rule, which says when this glyph is the last glyph in a word, do a final substitution, change the form, the standard form, into the final form. And I'll try to just show you that in a typing demo, and I'll do a few of these. So I will switch to my Mongolian keyboard, which you can't see. And what I'm doing is I'm pressing the E key for eche, for the first letter. And so there is the independent form of E. And if I press another letter, C for the ch, you can see that the initial form adapted dynamically into the independent form adapted dynamically into the initial form. And we have this final form of ch in the second place. And then if I put the final E, it comes straight in as the final form of the letter. So I pressed E, and here is E again, and here is E again. So this letter E has three different realizations, four different realizations, in fact. Here is E as an independent form. This is E as the initial form. This is the medial form and the final form. But these are all the same Unicode code point. So if I convert these code points, it's all this code point 1821. And it is this power of glyph substitution, which is contextually determined, which is allowing us to create the effect, the requirements of the writing system, but keeping this standard Unicode layer consistent. Now, slightly outside of the font responsibility is this concept of reordering, which is really a responsibility of the rendering system out in the application or operating system. So in this case, we have something that looks familiar. We have this vowel sign E, which is on a dotted circle. And so you might think that this is placed with an anchor. But because this particular vowel sign appears to the left of the consonant which it is modifying, it takes up space on the line of writing. And because it takes up space, we need to accommodate that in the writing line, rather than the marks that went above and below, which are a little easier to deal with. So this letter itself needs to move. Unicode defines, in this case, that the text is stored in what's called logical order. So we have the consonant, which is la, and we have the vowel sign, which is I. And the pronunciation is li. And so the storage order is logical order. We get the code point for la, followed by the vowel li. But in order to display this, we need to have the vowel move to the left of this consonant. And so it is the job of this rendering layer to reposition this short vowel I to the left of the consonant, and then the font must be aware that that's going to happen. So let's look at that in practice. If I type, if I switch to my Devanagari keyboard, if I type the ka, we get that. And if I type the I by itself, we get it over here. But if I type the ka and the I, then I had, as the typist, I typed it in the phonetic order, but the rendering system pushed the font for the I onto the left of the ka. So that is reordering. And there is a great deal more complexity to fonts, but for the purposes of today, I don't want to go into, we don't have time to go into too much detail on the full range of things that you can do. There's a lot of stuff in addition to the substitution and the positioning that affects the appearance of fonts, such as font variations and color fonts. but these are really outside of the scope of the core linguistic requirements. Now, what I would say on the positioning and the substitution, there are these basic rules. A becomes B in a particular context. As one member of the community, Bedad Asfabad, has shown, you can actually build a Turing machine based on those substitution rules. And so really the possibilities of what you can do with the font technology are really quite incredible. Let's talk about keyboards. So as we said, the job of the keyboard is to get language into a computer. Unlike the font, where we expect to have a very consistent visualization, allowing for stylistic changes, but a very consistent visual representation from the Unicode layer. When it comes to input, we actually know that there are a diverse range of ways that people approach their writing and the way that they think of their own language. And so really embracing that diversity means that we want to have input systems that allow a range of inputs to get funneled into the very consistent Unicode layer. And so it's this really, the key job of the keyboard is to manage that conversion. Let's talk about different types of keyboards. I think we could call the general category here input methods, keyboards being one of them. So the simplest keyboards are really typewriters. You press one key, you get one output, and everybody is familiar with this. There are cases where you can set up a keyboard. The Javanese keyboard in Windows has the letter Q, and that outputs 2 Unicode values from a single key press. And so you shouldn't be constrained in your thinking that a single key press can only output one code point. And we are also deeply familiar with the basic modifiers such as shift, in which you access a different code point, not 65, 0065, but 0045 to get the capital. And so the keyboard is taking the combination of 2 keys and outputting a different value. Things get more interesting with these traditional keyboards when we think about dead keys. In this case, you can take a modifier key, such as the alt graph, and so you press that and then the hyphen, and then you can press the vowel that you want to put it on, and that allows you then to direct the output to a different code point. So let me just show you how this works. So we can press, I'm pressing the right alt key, which is a traditional keyboard modifier key on Windows systems. And I'm pressing that and the hyphen key at the same time. I'm sorry, you can't see this on my, while I'm typing, but. So now I've put the keyboard into a state where it's waiting for the vowel to come. And I could press the A key and I would get a macron over the A, but if I press the E key, oops, I'm in the wrong keyboard. I'll do that again. So I press the Alt GR key and the hyphen, and then it's waiting and it will take the next vowel. But if I do it over the E, I get the E with the macron. There's a few more things I can do. I can map 2 code points to the R key. In this case, you can see that I had 2 code points there. And the other thing that I can do with this Alt GR, this dead key mechanism, is that I can start to stack. And we saw some extreme stacks in Debbie's talk. So in this case, I can type an A key. I can add the diresis Oops, I have to remember how to type this. And then I can also add an acute accent. So I'm going to do the Alt-GR key, in this case, a comma, and then the acute sign to put an acute above that. For this particular example, I'm using the English India keyboard, which has a lot of the diacritics needed for writing Indian languages in the Latin script. Let's talk about our next category of input methods, and this is IMEs. And I won't say much about these. These are really very specialized pieces of software that solve ambiguity during the input process. So in the case of Chinese, Japanese, Korean, and a number of other languages and writing systems, the character set for the orthography is so big that it doesn't fit onto a normal keyboard. And moreover, there is a lot of ambiguity in the signs that you would express with a common phonetic form. And so in this case, if I press M-A, ma, a phonetic realization in Chinese, there are many, many characters that could be written with that pronunciation. And so the IME provides a candidate list for all of the different ways that this syllable could be written. Now, IMEs have also been developed a lot of other systems for resolving this ambiguity, such as language models and text prediction systems to try to help speed up the process. But let's look at really an example of this working. And I will remember to switch to my Chinese input method. So I type M followed by A, and you can see this window pops up, which allows me to navigate and see all of the characters that could be written with this form. And there are pages of them. So then I can pick a form such as this one, and enters that text. So IMEs are really, because of the fact that they show this UI to the user and they have these built-in language models, they are very much more complex pieces of software and outside the scope of most people creating them. But there are, I will link to some instructions about how to do that at the end. Now, to me, actually, a much more accessible technology is really complex input methods designed to support complex orthographies. And I'm not sure that we really have an adequate name for this kind of input method. But one way we could refer to them is deterministic input methods. And Keyman is the product that has really established this category quite some time ago. What this category does is it's really like the substitutions capabilities in a font. We have transformation capabilities in a keyboard. The ability to understand the context of what is being written and to adapt what is being stored in the Unicode layer. The classic case of this kind of a keyboard, a need for this kind of a keyboard, is in Sinhalese. The Sinhalese national keyboard standard is called the Wijasekara keyboard, and it has this very specific requirement that is in tension with the way that Unicode is encoding the Sinhalese script. So we saw earlier that this phenomenon of reordering, and these vowel pieces which sit on the left side of the consonant that they modify. So this is the syllable. This one in the middle is the syllable K, I think. And this piece of the vowel is modifying this sign, which is the consonant Ka. And it becomes Ko when you put this vowel lengthener on the end. So the process here would normally be that you type the consonant and then the vowel. But that is not how this typewriter evolved in Sinhala, in Sri Lanka. Because before there was Unicode, people just typed in visual order, left to right. And so they would type the vowel sign and then the consonant. And so there is the expectation today that you should type in what's called visual order. What this means is that the keyboard has to understand that the vowel being typed now doesn't combine with something that's already been written, but needs to wait for the next consonant. And so this requires the keyboard to put in this special character 200C and then the vowel. And then when the next key press comes in and it's a ka, it can delete what it had already stored and put in the sign for ka, which is this D9A, followed by the same vowel that we had up here. And then when this vowel lengthener comes in, the ka remains the same, but the pre-base vowel can get replaced with the split vowel, the O, which is ODDC. So let me show you how that looks. Switch to the Sinhala keyboard. And so we type the pre-base vowel. And if I convert that, you can see that's ODD9. And there's the 200C. So we do the pre-base vowel. And then we have the ka come in, which is that one. But if I convert to code points now, you see the ka remains the same, but ODD9 was on the right side of this. So F, L, and now if we press the D sign, that lengthened it, but that converting that is this sign ODDC. So that's how this is supposed to work. As you can imagine, to achieve this, you write a lot of these kind of substitution rules, and there are other ways that you might express that as well. There's a lot you can do with this kind of keyboard. One of the interesting capabilities is that you can approach what IMEs provide by having setting up cycles. So when you have ambiguity in the input system, you can allow the keyboard to detect the context and forward it to the next state. And so I'll just show this kind of a case where if I'm pressing the Alt-GR key and the H key, oops, with the correct input method. This is an Egyptian input method, which is something I wrote. And so I can get the H with a dot. And if I do exactly the same key press again, I can press the Alt-GR and the H again, and it changes the dot into the breve below. And I can go back and do the same key press, Alt-GR and the H, and get to the macron below. And I can go back to the beginning to the dot. And so that allows me to select the form of the sign that I want to show. And then I can convert it. And so this this Egyptian input method has a lot of the large character set qualities of, say, Chinese or Japanese, but it doesn't need a full IME because it's possible to create deterministic rules that qualify how to enter everything. I will just have one more demo, which just shows you sort of the breadth of the capabilities of the combination of open type fonts with the substitution rules and positioning rules and a complex keyboard system. So in this case, we have a block of 6 Egyptian signs, and I can type J15, which is the way to access the top sign. I can convert that. I can add a joiner This is now, as of Unicode 12, we have these joiners which describe the blocking of an Egyptian cluster. I can type Z11, which is the sign here. I can type a horizontal joiner, and I can start a nested segment with a segment start. I can do the face with D2. I need another horizontal joiner and another nested segment. And now I can do the T, and now I can do a vertical joiner, and I can do the R character, and I can end one of these segments, and now I can do a final vertical joiner and N25 to finish and end the segment. And so putting all of that together, a lot of complexity in font substitution rules and a lot of complexity in the input system allows us to really create a very natural experience for typing something complex like Egyptian in a way that we hope people will be able to use and benefit from. So a few references, a tool for creating typewriters, Keyman developer tool for making these deterministic input methods, a link for how to author input method editors, which is not for the faint of heart, and a bit more information about Windows keyboards. Thank you very much.
All right, now we can move to our Q&A. I think we have just a few minutes, but thank you to everyone who submitted questions prior to the event. We got plenty of questions, which is great to see. We'll address the questions that are more general or more broadly relevant. And for those of you who have specific questions about a character or script, we encourage you to use our issue form or other resources, and we'll provide those links at the end. Now we'll start with the questions. The first one is, can you talk about right to left problems as well as combining superscript and subscript symbols? And this was submitted by Ilan Gonen. Andrew?
Sure, I'll have a go at that. So right to left is a property of the characters themselves. And so each character in Unicode identifies whether it is a right to left character or a left to right character or something in between, a neutral character. Responsibility for laying out text left to right and right to left is really at the text layout level, not at the font level, and not at the keyboard level. And so it's really a little bit outside of the scope of what we're trying to cover today, and I think really warrants a dedicated conversation like this to think about BiDi issues, because they're fascinating and complicated. So I think the real answer to that question is let's talk about that more in depth another time.
Okay, great. I think we have time for maybe one more question. So this is, how do you add a character or code point in an existing script? This was submitted by Mohammed Mamoun or Rashid. So Debbie, would you like to answer that?
Sure. To add a character, you want to use that template that I pointed to. So add a character to an existing script. You don't have to provide a code point, because the script ad hoc will help provide we'll look through, make sure there's nothing at that particular spot. And there's some tips in the template that I shared. So that's how you add a character. You have to propose it.
Okay, great. Thank you. So I think we should start to wrap up. Maybe we can have time for one question if it's quick. So this will be for you, Andrew. First, I'll read the question, but just try to summarize how you're interpreting it, how you're parsing it. So is there a way to develop a Unicode that combines characters within languages with transliteration, a language like Arabic? And this was submitted by Olan Revaju Samuel.
Yes. So what I'm understanding there is I think the desire is to type transliteration and see the results in a script. And I think absolutely you can do that with Arabic. And I think the technology to look at is this deterministic input system, this kind of keyman style capability, where if you receive an A event from a keyboard, you can choose to show it as the Aleph character. And so you can output a Unicode Aleph code point. And by taking into account all of the contextual variation necessary, you might want to evolve and might be able to evolve a complete transcription input system for Arabic using Latin letters coming from the keyboard. I have written such input methods for Indian languages where a K followed by an H inputs the single Unicode code point for a Ka, the aspirated vowel. So absolutely, please look at these deterministic input methods, the schema style.
Okay, great. So let us close out today. I want to thank Debbie and Andrew for presenting and answering our questions in this Q&A session. It was great to hear all your insightful answers. And thanks for Karen for all the logistics today and leading up to today to making this event possible. And finally, thanks to all of you in attendance for making this event a success. All of us are really, really ecstatic to see the interest you've shown in documenting and preserving languages. We plan to have the recordings for this event available in the coming weeks, and we hope you stay connected for more information, future events, and can share this information with your colleagues. For general questions regarding Unicode, please visit home.unicode.org, or for specific questions or issues, use our contact form at unicode.org/reporting.html. And there have been plenty of great questions, so please definitely take the opportunity to reach out. And we hope you all have a great rest of your day. Bye.
Great. Thank you very much, everyone.
Thank you.